All right. So here is the next lesson for implicit differentiation for my students. Hopefully you're watching this on Monday, the day that we first learned about implicit differentiation. So that way you can then be prepared for tomorrow's, class, where we'll just be kind of working on the homework and stuff like that. For other students, you'll be hopefully watching this on Tuesday or some other future day, just to kind of catch up on whatever you missed on the second day of implicit differentiation. So we're going to jump right in, okay, to our, what we're going to cover today. It's really 3 examples, but they're going to be pretty meaty, okay? At least the last 2 are. The first one's going to be a little bit tricky too, okay? So again, the name of the game here is implicit differentiation. How do we know that we're going to be doing implicit differentiation here? Well, so we're being asked to find dw dt, and if we look over here, we have a variety of t's and w's kind of mixed together on both sides of the equation, and there's not going to be some easy way to rewrite so that we have w in terms of t here. And so essentially we're just going to have to take the derivative as we see it. Keep in mind that we're taking the derivative with respect to t. So t is like our x here, w is like our y. In fact, if you run into problems with this, if like the different variables kind of mess you up, you can feel free to rewrite your problems for yourself. So for example, dy over dx in this case instead of dw dt. And so anytime you see a sine of w or cosine of t, you could just say that's 2 sine of y cosine of x equals tangent of 2x squared plus secant cubed of 2y. And then you could take the derivative as you see it right there, but then of course just make sure you rewrite your answer back in terms of w and t at the end. Okay, so if you prefer x and y's, you can rewrite it, temporarily, but then make sure you put it back in the correct spot, or put it back in the correct variables at the beginning. If you don't want to have to rewrite it back in the normal variables, you could just say in your work somewhere, let w equal y and t equal x, and that'll allow you to get away then without having to rewrite things in your work. So if you say this, then you can rewrite your original equation there in terms of x, y, and then solve it as you normally would, and that should be fine too. Okay, that way you don't have to like reinterpret it back into terms of w and t. We're going to stick with w and t though because that's what's written there. Okay, so here we go. So when we go to take this derivative here, something I notice on the left-hand side here, I see a product of sine and cosine. So we're going to need to use that product rule over here. Over here, I see tangent, for example, of 2t squared. Remember that 2t squared is in parentheses. Okay, so that's going to be an application of the chain rule. And then secant cubed of 2t, again, if you want to think of this, it's really secant of 2w, secant of 2w cubed, like that. Okay, so helpful to look at that way. Again, another application of the chain rule. I'm going to start taking the derivative here of the left-hand side. I'm going to, since it's a product rule, I'm going to consider the 2 sine w as my first function, the cosine of t as my second function. Okay, so when we go to take the derivative of this, it will be the second function, so cosine of t. And yes, I'm going to start over here because it's going to be a long line here of work. So cosine of t times the derivative of the first, so the derivative of 2 sine of w is going to be 2 cosine of w times the derivative of what's inside. Since we're differentiating w here with respect to t, times the derivative of w is going to be dw over dt. Okay, so the second, cosine, times the derivative of the first, 2 cosine w times then the derivative of what's inside, dw dt. Okay, plus the first, 2 sine w, times the derivative of the second, derivative of cosine, negative sine of t, times the derivative of what's inside. The derivative of t with respect to t, just 1, so I'm not going to bother putting a 1 there. Okay, so there's left-hand side, product rule. Okay, second times the derivative of the first, plus the first times the derivative of the second. Then over here, we'll take the derivative here. The derivative of tangent of 2t squared, the outermost layer is tangent. The derivative of tangent of something is secant squared of that something times the derivative of what's inside. Derivative of 2t squared is 4t. The derivative of t with respect to t is going to be 1, so it's just 4t there. Plus The derivative of the cube of something is 3 times that something to the second, okay, times the derivative of what's inside. What's the next layer inside is secant. The derivative of secant of something is secant of that something, tangent of that something, okay, times the derivative of what's inside that. The derivative of 2w with respect to t is 2 dw dt. Wow, and I am off the screen. There we go. I can barely fit it in there if I zoom it out. One more skosh. All right. So there's our derivative. There's our equal sign. Okay. So again, with the tangent of 2t squared, derivative of tangent is secant squared of what's inside times the derivative of what's inside, 4t with respect to t, so it's just 4t. Okay. The derivative of secant cubed, something cubed, is 3 secant of 2w squared times secant of 2w times tangent of 2w, right? Because the derivative of secant is secant tangent, so secant 2w, tangent 2w, times then the derivative of 2w, which is 2 dw dt. Okay. The nice thing about this video, for you for the first time that are watching, you can feel free to pause it, rewind it, slow down and stuff like that, just to see where, I change things up and stuff like that. And of course, you can feel free to ask me questions about it tomorrow in class too. All right. Now we have to isolate dw dt because we're trying to find dw dt. So here's a term with dw dt. And here's a term with dw dt. Okay? So I'm going to bring everything over to this side. Cosine t times 2 cosine w dw dt. I can't really do anything simplified with that. I'll bring the 2 out front and make it 2 cosine t cosine w times dw dt. This I'm going to move over to here. So I'm going to bring this over. It's now going to be a minus 3. So minus 3. This is secant squared of 2w, but I also have a secant of 2w right here. So if I multiply those together, it's actually going to be secant cubed. So I'll put those together just to save myself some writing. So secant cubed of 2w. And then I have the tangent 2w. And then I have the 2 dw dt. I could have multiplied the 2 and the 3 together there. If I wanted to, the 2 with the dw dt times the 3. Could have made that 6. And maybe I'll just go ahead and do that. I'll go ahead and just make that 6. Okay. So now I just have the dw dt along for the ride there at the very end. Okay. Equals, I'll leave the secant squared here. I'll put the 4t in front though. 4t secant squared of 2t squared. And then it's going to be a negative 2 sine w sine t over here. So if I add it over, it'll be plus 2 sine of w times the sine of t. If you'll allow me, I'm going to go ahead and factor out the dw dt and then divide what's left over to the other side. So I'll have dw dt equals, we'll have that 4t secant squared of 2t squared plus 2 sine w times sine of t all over, and then again, we just take out the dw dt, so this quantity is going to go into the denominator here. So 2 cosine t cosine w minus 6 secant cubed 2w tangent 2w, like that. Okay, so there's our derivative. All right, a little bit of a mess with all of the derivatives and things, the chain rule applications. That's the messiest you should really expect it to get right there for finding that first derivative. But there it is. Okay. Again, we factored out those dw dt's right there to allow us to then divide over this piece over to here and get that derivative. All right. So again, if you had questions on this, feel free to rewind, rewatch it, or rewatch the parts where you got lost or whatever. And then feel free also to ask me in class tomorrow too if you have any further questions. Okay, that's fine too. All right. Moving on. Okay, 7 and 8, we're going to be looking at similar situations here. Okay, what does this mean? When you see d squared y over dx squared, that is the second derivative. And so we'll take our function right here, which we know, hopefully you recognize as the circle, right, with radius of 5, and we'll take the derivative of this twice to get the second derivative. Okay, so let's take the derivative here with respect to x. So the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to y is going to be 2y times the derivative of y with respect to x, right? That dy over dx there by that chain rule. Derivative of 25, 0. Okay? Now at this point we have two options. Option one, we can solve this first derivative, okay, or the first derivative we took here, we can solve it for dy dx, and then take the derivative again once we solve for dy dx. Option two is we could take the derivative again as it's written. This will also allow us to find the second derivative. For this one, I'm going to go ahead and solve for dy dx first, then take the derivative again. So I'll subtract the 2x over. Okay, so we get 2y dy dx equals negative 2x. And then divide both sides by 2y. The 2's will cancel, and negative 2 and 2 will cancel to leave us with negative x over y for our derivative there. Okay, that's our first derivative. So then if I want to take the derivative again, well, the derivative of y with respect to x, if I take the derivative of that again, it's going to simply be the second derivative, right? D squared y over dx squared. The derivative of the first derivative is the second derivative, so there it is. The derivative of this, what rule do we need to use here? I know I'm asking an empty room, but hopefully you're answering in your head at home or in the comfort of wherever you are listening to this. It's the quotient rule. So it's the bottom, y, times the derivative of the top with respect to x, so negative 1, minus the top, negative x, times the derivative of the bottom with respect to x, so dy over dx, for the derivative of y with respect to x, all over the bottom squared. Okay? Now, typically we don't stop here. We technically have found the second derivative, but if you look within that second derivative, we have dy dx. A typical directions here, in addition to saying find d squared y over dx squared, typically they want you to do it in terms of x and y. Oops. Those are typical directions. Find the second derivative in terms of x and y. If we look at our second, we have the second derivative right now, but it's not in terms of x and y only. It's in terms of x, y, and dy dx. And so this will not have answered the question. So how can we rewrite this in terms of just y and x? How can we get rid of this dy dx? Well, what do we already know dy dx is equal to? Dy dx is negative x over y. This dy dx is this dy dx in this problem. And so I'll go ahead and make that negative y here, minus, make it a plus x, minus negative x. And then instead of writing dy dx, we can just write negative x over y, all over y squared. Okay? And we could simplify that more if we really wanted to. We could get a common denominator. We could multiply the x and the negative x. We could get a common denominator in the numerator. Instead of dividing by y squared, we can multiply by 1 over y squared, so on and so forth. But right now, we'll just leave it at that. Okay? We won't worry too much about the simplification for that right now. I'm just worried about you guys being able to do that second derivative. But there it is. Okay? There is the second derivative. Okay? Now again, this is one option we had for finding that second derivative. Alternative to what we just did right here, I could have taken the derivative of this at this point. It would look something like this. The derivative of 2x is 2, plus, to take the derivative of this, it would be a product rule. So it would be the second times the derivative of the first, so another 2 dy dx, plus the first, 2y, times the derivative of the second, so d squared y over dx squared, equals, and then the derivative of 0 is still 0. Okay? I could do the same thing I did before, where I had a dy dx, I plugged in negative xy. Here for these dy dx's, I could plug in a negative xy, so it would be 2 times negative x over y, times 2 negative x over y plus 2y, and then I could solve for d squared y over dx squared. Okay, so I could move all of this stuff over, subtract this quantity over, and then divide both sides by 2y, and I would end up with a similar solution to that. Okay, it won't be the same. They'll be equivalent, but not obviously they won't look exactly the same. Okay, so that is how you find that second derivative. So I'm not going to continue on with that one, but that's another way to do it. So again, option one, take the derivative once, solve that first derivative for dy dx, then take the derivative of both sides again, and wherever you have a dy dx left over, plug in the old dy dx you had there, negative x over y, boom, there's your second derivative. Or take the derivative of that first derivative right away without rewriting it. Again, plugging back in the negative x over y, which of course, in this scenario, right, we didn't solve this one for dy dx. So you have to solve this for dy dx to get the negative x over y and plug those in, and then eventually solve for d squared y over dx squared by moving, algebraic manipulation there to get the d squared y over dx squared by itself. So that's an option 2. Okay? All right. Finally, number 8. All right. Again, if we go look at this, we want to take the second derivative. We're going to evaluate it now at the point 2, 3. And so we've got our situation here. This t squared y, when we go to take the derivative of that, we're going to have to use the, hopefully you said product rule, because that is what we need to do there. It's t squared times y, so it'll be a product, okay, derivative of a product. Natural log, we know how to take the derivative of that, and 6t. In this case, right, y is like y, and t is like our x. So anytime we take the derivative of t, it's like taking the derivative of x. Anytime we take the derivative of y, it's with respect to t, so we'll end up with a dy dt in there somewhere. Okay, so let's take the derivative of this product here. So the second times the derivative of the first plus the first times the derivative of the second, derivative of y with respect to t, dy over dt. The derivative of the natural log of something is 1 over that something times the derivative of what's inside, but the derivative of t minus 1 is just 1, so we don't need to worry about the chain rule there. I mean, it's there, but it doesn't do anything. And the derivative of 6t with respect to t is 6. Okay, now, at this point, we have the same kind of pathway to follow as we did for example 7. Either we can isolate dy dt by solving for dy dt here, subtracting these quantities over, dividing through by t squared, okay? And then take the derivative for a second time, or we can take the derivative for a second time as it's currently written. Now, I'm looking at this right now, and I'm thinking to myself, if I move 2yt over, and then move this over, and then divide everything by t squared, I'm going to have like a quotient and a product rule, and it's just going to be a mess. Okay? Right now, this looks a little bit more easy for me to take the derivative. So I'm actually going to leave it in this format and take the derivative here. Okay? So this will be another product. So the second, 2t, times the derivative of the first, derivative of y with respect to t is dy over dt, plus the first times the derivative of the second, so 2, plus, this is another product rule here, t squared times dy dt. So it'll be the second, dy over dt, times the derivative of the first, 2t, plus the first, t squared, times the derivative of the second. What's the derivative of the first derivative? It's the second derivative. Okay? Plus, 1 over t minus 1, I'm going to think of that as t minus 1 to the negative 1. Right? 1 over t minus 1 is t minus 1 to the negative 1. So when I take its derivative, I'll use the chain rule. Negative 1 will go out front. T minus 1 to the negative 2 times the derivative of what's inside, but it's just going to be a 1. You can put a 1 there if you want. Equals, and then the derivative of 6, 0. Okay, now, we have these dy dt's, and there's our d squared y over dt squared. But the beauty of this is that we're just evaluating at a point, right? Since t and y are our variables here, t is like our x, y is like y. So that 2 is a t value, that 3 is a y value. So anywhere I have t's and y's, I can plug in 2 for a t, 3 for a y. That still leaves me with my dy dt's, though. I need to figure out what those values are. How can I figure out what dy dt is equal to? Well, if you thought or said out loud, plug 2 and 3 back into the first derivative and solve for dy dt, you're right. Okay? We're going to plug 2 and 3 in here to get dy dt evaluated as 2, 3, and then we can plug that value in for the dy dt's here and here. So let's do that right now. So y times 2t is going to be 3 times, 2t is going to be 4, so I'll just go ahead and make that 4, plus t squared is going to be 4 times dy over dt, plus 1 over t minus 1. 2 is t, so 2 minus 1 is 1, so it's 1 over 1, so just 1. And that equals 6. Okay, so this is 12 plus 1, which is 13. Take that 13 away from 6, it's going to be negative 7. So we get 4 dy over dt equals negative 7. And so we get dy over dt equals negative 7 over 4. So now we have that value, and so we can plug all these values in and finally solve for this d squared y over dt squared. So Plugging in 2 for t again. 2 times 2. dy dt, negative 7/4. Y, 3 times 2. dy dt, negative 7/4. 2t, 4. I'm just going to go ahead and make that 4. 2 times 2 is 4. I could have done that there. I don't know why I didn't. T squared is 2 squared, so 4 times d squared y over dt squared. That's what we're solving for, right? Find d squared y dt squared. Plus, and then let's see here, negative 1 times, let's see, t minus 1. So 2 minus 1 to the negative 2 is still going to be 1 times 1 equals 0. Okay. So let me simplify the sum. 2 times 2 is 4 times negative 7/4 is negative 7 plus 6. Negative 7/4 times 4, negative 7, so minus 7, plus 4d squared y over dt squared, and then minus 1 equals 0. Negative 7 plus 6, negative 1, minus 7, negative 8, minus 1, negative 9. So it's negative 9 over here. I'm going to add that 9 over. We'll have 4d squared y over dt squared equals 9. Divide by 4 on both sides, d squared y over dt squared evaluated at 2, 3 equals 9 over 4. Okay, and there's our final answer. Oops, I think I should have gotten a negative 9. Let's see here. Negative 7 and 6 is negative 1. Minus 7 is negative 8. 9, but we're going to add it over, so plus 9. Nope, it should be positive 9/4 there. Yes. Okay, positive 9/4. And so there is the value of our second derivative. Okay, evaluated 2, 3. All right. So again, if you have any questions on that, feel free to rewind the video, replay it, to parts where you maybe got lost or something like that, and I can re-explain it. And of course, if you have any further questions, feel free to bring them in tomorrow in class when we have opportunities to work on our homework. Yeah, and so we'll see you tomorrow.